So this week I'm very pleased to introduce Dominic Walliman. Some people might know him as the Domain of Science guy. Other people might know him as the Professor Astro Cat books author. So Dominic was trained in physics and worked at D-Wave for a while. He settled down in Vancouver and started trying to promote and communicate science, and he's become well known for his graphics and YouTube videos and stuff. And when we chatted with him about coming to speak to us, we decided the best thing to do was some combination of the content that he works on and some discussion of how he does what he does and how he, makes a living and that sort of thing. So Dominic's going to sort of give us an overview of Domain of Science. So Dominic, it's all yours.
All right, thanks very much. Hello, everyone. Thanks for coming to the talk. So I was just going to expand a little bit on my background. So basically, I split my time now between two things. One is the YouTube channel, and the other is the Professor Astro Cat books, which I write. They're illustrated by a friend of mine, Ben Newman. And basically, my background started off in research. I did a PhD in condensed matter physics, specifically on superconducting quantum devices, and then got a job at D-Wave, which is why I moved to Canada. I'm originally from the UK. And then after working there for about 4 years, I quit to do YouTube. And since then, so over the last 5 years, I've been working on videos and growing the channel. I've got currently 850,000 subscribers and about 30 million views so far, which I looked up yesterday and I didn't I didn't know I had that many. So that's kind of cool to think about. And then the books are aimed for kids. So my YouTube channel is all for grown-ups, but the books are aimed for 4+-year-olds or 7+-year-olds, and they're very detailed books. Kind of. So this one, Atomic Adventure, in the middle. That one is basically a summary of the entire field of physics, but aimed at a 7-year-old. And there weren't any other books like that, so I really wanted to do that. I'm really proud that we managed to actually get that finished and published. So yeah, if you've got any youngsters who might be interested, or you want them to get them into physics, then that's a good book for them. So yeah, this is how I split my time now. And I thought I'd talk about why I'm doing science communication after having done a PhD and gone from research and professional science into that. And there's many reasons why I think science communication is very important, but I want to just focus on my top 3. And the first one is that all science is publicly funded. So in fact, all of this donut of knowledge is one of the videos that I've made about basically tying together all of the different this is like the most zoomed out map. So a lot of my videos are summaries of different disciplines in science and breaking them down into their sub-disciplines. I find that's a useful way to explain science because it helps set context of how things fit together. And pretty much all of these areas of human endeavor are publicly funded in some way, but with some of them, like literature or art, architecture, they are accessible to everyone. The technical details you need to learn about, but anyone can appreciate them. But there's a lot of things in science, because it goes into an abstract realm, and there's also true of like computer science and mathematics, which we've also focused on. Because it's abstract, there's a barrier to entry. And so as all of these things are publicly funded, it's sort of our responsibility to explain them back to the people who are paying us to do it. So that's one reason why I want us to do science communication. Another reason is I just really like studying a general realm of information. Like I'm quite a generalist. I'm interested in lots of different things. Also, for funding, science is obviously in competition with lots of other things. So I feel like science communication is a good way to make science stay relevant. So sort of a bit of a marketing PR arm of the scientific endeavor, which I think is important just to make sure it stays relevant. I actually think science and technology do a great job of that already. So the second reason is just to share my love of science. Basically, I've really got a lot from learning about science and learning about the way the world works, how the universe works. And I want to pass that on to people who don't necessarily have the ability to spend the time and energy on the higher levels of education. So I came into science in a bit of a strange way. I actually dropped it in school because I found it quite boring. And then I got into it later through popular science, through a show, it was on Channel 4 in England called Universe. And it blew my mind just thinking about when it was telling me about cosmology and things like neutrinos. And that got me really excited and interested in it. And this is all stuff that they weren't teaching us in school. And when I went and did a degree in physics, suddenly I was learning things like relativity and quantum mechanics, which I thought were, this is the interesting stuff. And I was like, we should always teach this stuff in school because that would actually excite people. And I think probably things are a lot better now than they used to be, but that's because so much more of this cool stuff is accessible to more people through science communication. And also, online videos are the way I focus my communication, just because online videos are a really good format because you can put a lot of investment into making one thing and then it stays on the internet forever, available for anyone in the world to watch for free. So it's a really good medium, I feel like, to be able to communicate science with. And then also on top of that, it's very visually rich, and so I can use the graphics and animations as well as sound design and music to enhance what I'm talking about. So that's why I choose videos to do my science communication. This is another one of my videos where I try to map every single kind of thing in space in one picture. And then the third reason I think science communication is very important is to try and fight disinformation, which I don't think requires too much justification these days. But with the political climate we're in, and also the climate that we're in, disinformation about science poses a real threat to actual people's lives in terms of, the vaccine and the pandemic, and also climate change. And this isn't a simple problem to solve. It's way bigger than, I don't really know how to solve it. It seems such a big issue, but at least I can do a bit towards it by promoting evidence-based thinking, and then also critical thinking, and highlighting those as important things. And I think the more people who are doing that, the better, really. So yeah, that's another reason why I think science communication is very important, to try and promote that kind of thinking as much as possible. And maybe that will help the fight against all of the disinformation, which has got a bit out of hand, I would say. Okay, so that's why I do it. Now let me talk a bit about my approach to science communication. So I'll be sharing a lot of these maps. So this is one of the ways that on my channel, the main and the most popular format that I do. So I take different areas of science and mathematics and explain them in terms of these large conceptual maps. And There's many different ways of doing science communication. I'm sure if you've been on YouTube, you'll see lots of different kinds of videos. I've done other videos as well, which explain just specific topics. So you could pick any specific thing like robotics or artificial intelligence and do one video just on that. But what I found was it's useful to actually sometimes set context and show how all of the bits of information that make up a field join together. And that's helpful because when you're learning something, it's easier to then plug new information in if you've already got a conceptual framework for where it will fit in terms of the other stuff you already know. And the main inspiring moment for this was when I was in lecture courses doing my undergraduate degree. And by lecture like 3 or 4, I was kind of lost about what we were learning and how it fitted into the course. And then halfway through a lecture course, say 6 or 7, you know, the professor was doing some derivation on the board, and I'm diligently copying down all of the equations, but I had absolutely no idea what we were talking about, why, or how it fitted in with anything else. And so I feel like a lot of people are in that situation, and often at the beginning of lectures you do get a list of the topics that will be covered, but I feel like a list is just like sort of one-dimensional, and the actual conceptual framework of information, like for example with this computer science map, it's helpful to actually put things sort of geographically next to each other, so that concepts that are similar to each other and most related to each other sit next to each other, and other concepts, there's kind of like a logical structure to how information in a field is structured. So they're nice because, for example, with mathematics, most people who haven't studied mathematics past, you know, age 16 won't know the full extent of what actually goes on in terms of research in mathematics and what the wider field of mathematics looks like, because mathematics is such an abstract and huge field that it's quite nice to actually have a map like this which sets the bounds on the subject, so that you know at least that you kind of know the extent of that subject. It's not completely endless, and unless you have something like this, this is really a hard thing to know. And then, yeah, like I said before, when you put things in categories like number systems or structures or spaces, you know, geometry and trigonometry are part of spaces which people will be familiar with, but then also complex analysis and differential geometry. Now they've got something to link those new subjects to, which they might not have heard about before, even though they've heard about geometry. So that's why these conceptual maps, I think, are a useful tool to explain science and basically any academic endeavor in general. And in fact, I would love it if there was a rule that anyone who's giving a lecture course has to start their first lecture with a map. It doesn't have to be as like colorful or well illustrated as this, but it could just be a conceptual map of what they're going to cover. So, and then each lecture they can refer back to that conceptual map and say, we're here and this is where we're going and this is what we're learning today. That would be my dream anyway. So that's my suggestion to the world. But yeah, nevertheless, that's what I'm doing in my little corner of the internet to try and help with that. There's also another thing which I hit on with these sort of the graphical description of information. Is that visual information is very easy for us humans to digest. So we're very visual creatures. You probably know that already. And we're also exceptionally good with visual memory and also sort of geographical memory. And an example of this is any one of us owns, I don't know, hundreds of objects of different forms, books and car keys and phones and whatever. And you can probably just name a random one, and we know exactly where our version of that is. So if I just said screwdriver, you probably know where you would get your screwdriver, or pack of cards. You'd probably know where that is. And so it's kind of amazing that our brains can hold in like hundreds of different objects without any effort whatsoever. I think it's kind of like an underrated skill that us humans can do. And it's also how memory champions remember sort of useless information, like several decks of cards that are all shuffled together, and they can just deal them out and memorize them all. And they basically do that by hacking our brain's visual memory, by making, you've probably heard of memory palaces, or kind of stories where they attach visual images. So each card represents a they've got a visual image that represents each card, and then they can just make up visual stories about how they're all linked together. Whereas if you're just given a list of, say, I don't know, 20 numbers, you'll probably remember the first 4 and maybe the last 3, and then you'll forget all the ones in the middle. And yet we can memorize hundreds of, we know where hundreds of objects are. So this kind of, these maps kind of tap into that kind of visual and geographical memory that we find so natural. So I think that designing information like this is useful to take advantage of that. And quite why, I'm not sure we're so good at that. I think it's probably something to do with our evolutionary history. Knowing where the best berry bushes are, or where we've stashed a load of food. I'd have to talk to an evolutionary biologist to know exactly the reason why. But the truth is it works, and that's very helpful. Okay, so that's my the reason why I do what I do and my approach to it. And so I thought I'd actually go into some examples of maps, specifically in physics, as this is with the physics department, and it's my background. And so I'll just take you through a few of my maps and then explain sort of the decisions I've made, as well as the science behind them, but also the decisions I've made in the design of them. I'm not really going to talk anything about the financial or career side of being a YouTuber, only to say that I think it's brilliant that the world is set up in such a way that actually you can make a living being a science communicator using YouTube and other things, and not just me. Like, there's dozens of us doing it, which is, I think, really cool. Okay, so this is the map of physics. So we're going to look at the map of physics, then I'm going to zoom into quantum physics, and then if we've got time, look at one part of quantum physics, which is the standard model of particle physics. So this map of physics is actually the first map video I did on my channel, and it was immediately popular. So I knew I'd hit on a certain format, which I think people enjoyed. And it's quite nice to, for non-physicists to have just one picture that summarizes the whole field and breaks it down. So it's split into 3 parts, as you probably know: classical physics, and then we've got relativity and quantum physics, which make up other distinct areas of research. So in classical physics, we've got all of the stuff pretty much before the 1900s, apart from chaos theory, which I think was developed mid-1900s. But with chaos theory, I figured it would still make sense for it to be in classical physics, just because it's definitely not quantum or relativity, although there is a bit of overlap with chaos theory and quantum physics. So it's never easy actually to include all of the different subdisciplines of a subject on a 2-dimensional plane. You can never like properly represent all of the interactions between all of these different disciplines, because often they're a lot more interrelated than you can just draw on a simple picture. But what I'm going for is just an introduction, so that someone who's not seen the who doesn't know in detail about the subject, they can get the first sort of lay of the land, and then if they delve deeper into it, then they can start learning about the nuances of things. And that's a general principle I take when I'm also writing kids' books. I don't want to limit myself to not talking about quantum physics just because I'm talking to a 7-year-old. I think there's an explanation about anything to anyone. You just need to be able to explain that thing in terms that they already understand, so they can fit it into their conceptual framework. But often the case is that you need to actually give quite a simplified description of the subject, which might be like a bit technically wrong, but it's still the first step in the right direction for them. And then as they learn more, they'll be able to like clean up the details and get more of the nuance. So that's kind of the aim with my maps. I can't give all of the different interrelated relationships between the different fields, but I can try and do things as best as I can. I don't know, let me know if you think there's any things that could get changed on this one. So I'll just talk you through the logic of this map of physics. So I started with the most basic, so laws of motion in Newton, and then universal gravitation and classical mechanics are core parts of physics. And then we've got optics, and then I put astrophysics and cosmology close to that because of the technology of it. Telescopes obviously use optics, and that was a big revolution in astronomy, was the invention of the telescope. And then I've put that next to relativity just because relativity tends to be with space stuff, so that sort of made sense. Even though there's a lot of optics also in quantum physics, so that's one of the links that this map doesn't quite capture. But you know, I think it kind of makes the most sense to be here. And then we have the laws of classical mechanics, fluid mechanics, waves, electromagnetism, which is also the same as optics, but it's not right next to it. But I guess I've done this also sort of a pseudo-historical sort of direction, from old stuff up there to newer stuff down here. And then I wanted to put thermodynamics next to condensed matter physics because they both use statistical mechanics as their underlying machinery. They use heavy use of statistical mechanics. So even though I never actually mentioned that in the video, I feel like just having that sort of relationship baked into the design of the image helps people learn kind of conceptually that they're related. That's my hope, at least. So that's classical physics. And then we've got relativity, which is fairly simple. Just the special theory of relativity and general relativity. And then we've got quantum physics with its subdisciplines, quantum field theory, which I've put in between special relativity and quantum physics because it actually combines the two. And then we've got particle physics, nuclear physics, and atomic physics, which is sort of like the basic description of atoms. And then we have the chasm of ignorance. So in my videos, I always want to make sure to highlight what we do and don't know quite clearly, as not to mislead people, because I think unfortunately sometimes with the communication, also marketing of science, some subjects can be a little overhyped. Well, that's not fair. I just say that sometimes it's not necessarily clear exactly what has and hasn't been proven with evidence. And I think it's very important we actually are very clear about that. And what's nice about being completely independent is that I've, not got anyone to please or prove anything to anybody. So I can be quite objective about what I talk about. So one example is string theory. I think if you talk to a lot of people who have maybe heard about string theory but don't know any of the details, I think a lot of people probably think that string theory is a core part of the laws of physics, even though despite all of its successes mathematically, there's no evidence to suggest that string theory is actually, anything to do with reality. So this is why I put this chasm of ignorance on. So this is the stuff we don't know, and the stuff on the other side of this chasm of ignorance. So there's mysteries that are still there to solve. And I also want to highlight the mysteries, because for any budding scientists out there who are looking at science and looking at what to focus on, it's the mysteries that really grab people's attention, because everyone loves a mystery, and it's also a possibility that you can actually contribute something to science. You know, people watching these YouTube videos might be the people that then actually crack what dark matter is, or dark energy, in the future. So I think that's good. I also made sure to, with the chasm of ignorance, to split quantum physics and general relativity away from each other, so that they're not touching, because that's the big thing that string theory is trying to solve, is a theory of everything that can get gravity and quantum physics to work together. So yeah, that's pretty much the map of physics and my thoughts behind it. I also put a section up here on philosophy, because this was sort of my route into physics as well, was as a teenager thinking about all of the big questions, big existential questions of reality, and reading in philosophy, and that directed me through to physics. And that's one of the things that I've enjoyed the most about physics, is that we've got many different descriptions about what the way the universe is, but the best one for me is the one that's got evidence and you can actually do experiments on. And so anyway, that's why I love physics and got into it. But I think philosophy is a thing that has got a big history with physics, and I think these philosophical questions are what drive fundamental physics to try and figure out the answers to what's going on and why. Although I don't think we'll ever actually manage to answer why, unfortunately. Okay, so now my slide's not working. So let's zoom in on quantum physics. So this one I did in 2020, this was last year. So you'll see my art style has moved on a bit and got a bit more complicated. But that's been fun too, is also to increase, sort of get better at doing illustrations and figure out how best to use Illustrator and the tools available to me. Oh, if some of you haven't seen my videos, basically they're not just these images and I talk through them. Every bit is animated. So each one of these, so let's just zoom in at the beginning here. Each one of these illustrations is its own little object. And so I'll begin just on one section and then animate them in while I'm explaining what they are. And then gradually build up the whole map. So not only does it have a geography to it, it's also got like a storyline to it as well. So yeah, that's what I do. So breaking down quantum physics, wow, what I wanted to do with this one was to sort of demystify the subject, because I think in popular consciousness, when people talk about quantum physics, people often focus on how it's mysterious and weird. And it's kind of frustrating coming from a quantum physics background, because I mean, we live in a quantum world. All of our devices, you know, this computer, the camera, the screens you're watching this on, that's all based on our understanding of the band structure of semiconductors, which is all quantum mechanics. So if we didn't know quantum mechanics, we wouldn't have any of the technology in the world we have today. And so all of this banging on about how mysterious and weird quantum physics is, I think, is a mischaracterization of the subject. And so that's what I kind of wanted to address with this video, is be a lot more pragmatic and down to earth and just talk about what quantum physics actually is. And so the field of quantum physics involves a lot of research areas like particle physics, nuclear physics, quantum chemistry, cold atom physics, and then lots of technology, quantum information, and that's all very pragmatic stuff, and stuff like MRI machines, which, you know, some of us need to go in sometimes, and it's useful to know where that stuff's actually come from. So the general design of this math for quantum physics, I'll just talk through that briefly. How are we doing for time? Oh, we're doing okay. So I started off just with the mysteries that sort of inspired people to try and figure out what was really going on at the atomic and subatomic realm. Was we had a bunch of these phenomena that we couldn't explain with classical physics. So I start off with those, and then a section called Quantum Foundations, which I'm not sure that's quite the right term for it, but it's basically just the standard body of physics that you learn when you do an undergraduate course on physics. So it's, you know, the wave function, particle wave duality, the Schrödinger equation, double slit experiment, Heisenberg uncertainty principle. And in this video, I couldn't really go into detail. Each one of these things I'm listing, it could be like a whole hours long lecture. So I don't have time to go into detail on each of them. So I'm always limited by sort of a one sentence description of what the Schrödinger equation is, or what Bell's theorem is, which is often quite challenging to be accurate about that. But I think what's useful about this is to just make sure that people hear the thing, like Bell's theorem. Now people have heard what Bell's theorem is, and they generally kind of know what it's doing, like why it's a useful thing to know about, and then once they know that it exists, then they can, if they find it interesting, go and delve deeper into other videos. And along with this video, I actually put a playlist together of lots of other videos on quantum physics, which expand on these topics. So yeah. So yeah, moving further down, we've got then quantum phenomena, which are this. So this is the bit where people are like, quantum physics is weird, because you've got things like entanglement and quantum tunneling. But notice it's actually just a very small part of the overall map. So the fact that these things are dominating the perception of quantum physics, I think, is a bit unfortunate, but what can you do? Then quantum technologies, like I said, lots of digital technologies, and then also things like lasers and superconducting quantum interference devices, which are the basis of quantum computers, which are very cool. And then, yeah, some other fields, quantum biology, I find fascinating. It's quite hard to do research in biological systems and actually tease out their quantum behaviors. So I find that very interesting. All of this stuff's interesting. I love it all. What's good about doing YouTube is, as a person who's interested in lots and lots of different areas of science, I get to actually spend my time doing the research and all of this stuff, which is what I found when I was doing academic research and also working at D-Wave. You have to be very focused on the task at hand. And so what's really nice about doing science communication is I get to actually satisfy my desire to just read very widely and learn lots of different things, and then waffle about them at great length to people who are willing to listen, which is always fun. Okay, so we've got nuclear physics, quantum chemistry, and then particle physics, which we'll look at in a bit more detail next. And then we've got quantum theory, which I placed around the middle of the map because it pretty much ties into everything. And then above that, the interpretations of quantum mechanics, which we're starting to get into the sort of foundational questions and the more philosophical questions. And then at the top right, quantum gravity, which isn't a thing that exists yet. It's our name for the thing we don't know about, but it's good to talk about because this is one of the mysteries. Well, the big core mystery, I guess, at the bottom of quantum physics, along with the interpretations, like what's actually going on, what's the actual fundamental reality of stuff in the quantum realm. Okay, so that's the map of quantum physics. Obviously, I had to skim over that. The actual video is about 20 minutes long, so if you want to find out more detail, I've got some links at the end to my YouTube channel and stuff like that. Okay, and finally, zooming in on particle physics. So this was a map of fundamental particles, which I wanted to make because it's just nice to know. There's, again, a lot of people have heard about the Higgs boson and the experiments going on at CERN and other particle colliders. And they also heard about the standard model of particle physics, but the standard model is actually quite difficult to get your head around if you're not already very knowledgeable about physics. And so what I wanted to do is try and lay out as much as I could in a diagram to help people get their heads around basically all of the fundamental particles, all of the forces that they follow, and then all of the conservation laws, so all of the things that mediate particle interactions. So what particles can interact with other particles, what is and isn't allowed. And so that's basically what this map does. First of all, I've got just all the standard model particles, and this is an image you've probably seen before. But this is actually a little misleading, or it lacks some the more subtle information, which I've expanded down here because the normal picture doesn't include antimatter particles and also doesn't include color charge. So when you add those in, each one of these quarks, this down quark, actually turns into 6 unique particles. And instead of just having one gluon, you've got 8. And so these are actually all the fundamental particles, not these. And there's a lot more than what you normally talk about. So that's my attempt to clear up one slight misconception. And then all of these particles follow the fundamental forces. So we have the electromagnetic field, we've got the strong field and the weak field, which correspond to the electromagnetic force, the strong force and the weak force. I don't have gravity on here because that was the whole big problem about general relativity and quantum physics not meeting, and why string theory exists, because people are trying to put gravity into this and haven't yet managed. So, but I do have the Higgs field, which is what gives all the particles mass. And so these are the different fields in quantum field theory that the different particles interact with, but not all fundamental particles interact with all fields. And so this was my attempt at a diagram. There's other ways of doing this, which I've seen, which are kind of quite complicated and quite difficult to parse with your brain. You have to keep looking at the kind of like forces in Venn diagrams with lines joining all the particles with each other. But I thought a simpler way would just to break it down. So you've got the electromagnetic field, and you've got all the particles, and then basically I've grayed out the ones that don't interact with the electromagnetic field, and I've got in solid color the ones that do. And one comment I got a lot was, why is the photon grayed out? Because surely the photon is made of electromagnetism, so it should exist. People thinking I made a mistake, but photons don't actually interact with other photons. So photons themselves aren't, that photons are the force carriers of the electromagnetic field. They're not the, they don't actually interact with it. They are the field. And then same thing with the strong field. You've got all the quarks and the gluons, and then pretty much everything interacts with the weak field apart from the gluons. And then everything with mass interacts with the Higgs field, apart from the neutrinos, which is weird. Neutrinos do have mass, but we don't know where they get it from. So that's a mystery. And then finally, in the middle, we've got some Feynman diagrams of all the standard model interactions that you can have. So this is, we've got the particles, we've got the forces that they follow, and then we've got the rules about how then particles interact with each other, because particles can split into other particles or join together to form new particles, which is how particle colliders work. And there's certain rules about exactly which can do that. And the diagrams show the kinds of particles and the kinds of interaction that those particles can form, and these can be rotated. And then the main rules about particle interactions are the conservation laws. So particles have many different properties, and these properties, so the simplest things we're used to are things like mass or charge. But there's many other properties as well in particle physics. And in an interaction, say a weak force interaction, all of these different properties are conserved. And so you need the same number coming out as went in. But you don't need to conserve these forces in weak force interactions. But you do need to conserve them in electromagnetic force interactions. And then strong force, you need to conserve everything. Although I have been told that this isn't actually true. Sorry, this isospin magnitude should be actually in here. It's not in the right place, but I'm a bit out of my depth with isospin magnitude. So I hope I haven't made a mistake, but I might have made a mistake with that one. So anyway, that's that. Again, a whistle-stop tour. The full video is about half an hour long. So if you're interested in delving deeper, go watch the full video. Okay, so that's everything I'll talk about. Hopefully it's given you an insight into sort of why I do what I do and the way I go about doing it. I've got basically a few links here to my YouTube channel. A big part of me funding my channel is actually selling all of these images as posters, and I sell them on a store on DFTBA. But I've also got the digital images which you can download for free and use for personal use. I wanted to make sure that they could be just available for anyone to download and use for educational uses. So they're all on Flickr. Just search for Domain of Science on there. And then, yes, Professor Astro Cat, you can find out more at that link. And on social medias, I'm just at my name. All right, thanks everyone for watching.
All right, thanks, Dominic.
Oh, I guess one thing is about how to be successful on YouTube. So part of the move from having a proper job to doing YouTube was actually trying to make money from it. And it was a bit of a risk to, I basically set myself a certain time frame that if I wasn't making an income from it, I'd have to give it up as a career or attempted career and go back and get a proper job. So one thing I really wish I had been told was to be successful on YouTube, you really need to do something different to everyone else because you need to somehow get over the hump of being obscure. And because you just need to be popular and you need to get lots of views. Unfortunately, that's just the way that marketplace works. And so in a way, I was fortunate that I hit on this map format fairly early on. But that's definitely a thing I would say to anyone else who's thinking about doing YouTube videos as a career, is to definitely try and find a unique way of talking about the subject that you're interested in. But also there's lots of people who do make YouTube videos without having it as a career. And in that case, you can just do whatever you want. It's interesting you say that. I hadn't really thought about that, but I think they're pretty. I mean, especially the map of physics. I think that would be very digestible to youngsters. Yeah, pretty young, I think. Some of the other ones, like the quantum physics one, I think it starts to get a bit too detailed. But just looking at it and just being exposed to those concepts, I think, you know, they would be like, I know people do buy the posters to educate their kids, or just at least have a thing on the wall that's showing them all of the different bits of a certain subject. So I think for the general posters like chemistry and biology and maths and computer science, I think I don't see any problems with those being just as they are for kids. But a lot of my focus for kids has been on the kids' books, the Professor Astro Cat books. And with those, what we've got the added element of our characters, like approachable characters. They're all animals, like Professor Astro Cat is just one of the animals. There's a few others. And then also little storylines too, right, that the characters undergo those storylines. And I think that's a great way to engage with youngsters, is through characters and stories and humor, which is things, obviously, I kind of have a story in terms of my videos, because I have a beginning, middle, and an end, and a logical progression from that, which is normally historically what got discovered first and what's current, like, mystery research now. As for doing videos for kids, unfortunately, it's really hard to get an income from it, and I have to be quite tactical about how I spend my time. And it's a real shame, actually, that YouTube haven't got some way of incentivizing people to make kids content, because it just means that there's not a huge amount of good quality kids content out there. In fact, if you go on YouTube and search for kids stuff, most of it's absolute garbage. So, yeah. That's something I think a lot of people are struggling to work out. And from what I've seen from people on who are science communicators in the media, like in news media, you have to be careful about not undermining people's views, even though you know they're wrong and misguided. People get immediately defensive if you point them out and call them stupid. You know, that only entrenches them, and it just increases polarization of all of this stuff. So as much as I know, I think the way to approach it is with compassion and be like, oh, that's interesting that you think that, without belittling them or laying into them for those views. And then just trying to start the conversation with them and explain your own point of view about how the world works and why you think that vaccines, say, are effective, and why taking a vaccine is better than getting COVID. Yeah, I was entirely self-taught, so I don't think you need any formal training. And the amount of information that's already online, tutorials teaching you how to film things, the equipment to use, and then the software to use, it's all online already. That's the whole, it's amazing how much is already online. I think the best advice is just to start making stuff, not have any barriers to trying to be too perfect too soon, because I think a lot of it is learning by doing, and also just being actively inquisitive about what works and what doesn't work, and why something works and why something doesn't work. If a shot doesn't come out correctly or like you were expecting, actually think about like what it is that made the thing not quite work. And so, yeah, with a lot of my videos, I mean, you could kind of see in the talk the progression from my my first drawings through to the design of my posters now, they've gone through an evolution. That's just from me making videos and then each time trying to come up with ways of improving those things. So yeah, I would say to anyone who's thinking about making videos is just to start making videos. And you don't need any special equipment. That's the other mistake a lot of people make, is they think, oh, I need to go buy a special camera and audio equipment. And the truth is you can do a load of stuff on your phone. I think the first thing to get would be to get a good clip-on microphone and something to record that clip-on microphone. And if you've got that and a camera, like your phone, that's all you need, really. Yeah, good question. So basically with my my process was I saved up money and I had about 2 years of runway where I could just live. I could pay for food and rent for 2 years, but then I'd wiped out all of my savings. So I needed to start making more income than I was spending after. Well, I was like, I'll give myself 1 year, and if it's going disastrous, then I'll give up then, because I didn't want to just wipe out all my savings. So that's what I did. And then in terms of how you make money on YouTube, the basic way is ad revenue. So YouTube serves ads in the videos. That's a pretty low amount unless you're getting, millions of views per month. That won't amount to much. The second way is sponsorship. So you probably have seen lots of YouTube videos where they've been sponsored by a certain company. And then there's merchandise. And so that's one of my main revenue sources, is that basically because I'm making images, I can then sell those images as posters. And so I partner with DFTBA, which is just a really good company because it's been set up in a way not to just make the most amount of profit as possible. It's been set up as a non-profit where they are giving as much money to the creators as possible. And then also any profits they get go to charity. I'm just lucky that that thing exists. If DFTBA didn't exist, I would be making less money, basically. So yeah, if you can get a good merchandise thing going, that's good. And then the other thing is crowdfunding as well. So a lot of people have a Patreon or some other crowdfunding. And I think that's pretty much it, actually. So some combination of all of those things. And each channel will have more or less of different ones. I know some channels that get all of their revenue from crowdfunding and they don't have to do any sponsorships. Some that are just about all sponsorships and some that are all just ad revenue. But the ad revenue ones tend to be people releasing daily content. So it tends to be more, not so much the science education stuff because there's so much investment of time to make good educational content. And then in terms of competition, I've never actually got any grants to do any of the stuff I do. I know some people have managed to get grants, but I think mostly they sort of cross over with sponsorship. So people who are sponsored by, say, the Bill and Melinda Gates Foundation to talk about vaccine rollout or climate change, stuff like that. So it's not completely, a grant should be no strings attached. Sponsorships are always some slight strings attached, which is also always something to be aware of when you're watching YouTube videos, is like, who's the sponsor and what's their involvement. And so, yeah, competition, I think, boils down to just the fact that YouTube is a very saturated market now. So 5 or 10 years ago, if you're starting on YouTube, you'd have the early lead where there's a big audience and not many people are doing things. Now, when I'm, looking at doing YouTube videos and I want to do something on, say, black holes, which is the next video I'll be doing, there's, 100 videos already on black holes. And so I need to figure out a way of making it different to those other ones. So that's where the format is important. So yeah, I'd say there's a lot of competition but it's just because there's so much content. And everyone's competing then to get the ad revenue and the sponsorship money. And I'm fortunate in a way that I've sort of decoupled myself from that a little bit because I sell posters. Yeah, so I'd love to do maps of everything, basically. So if it keeps going, I can happily just do this into my retirement, basically. We'll see how it goes. Basically, the reason I haven't is because I've stuck with stuff I know the most about, because related to your second question, the length of time it takes to make a video is heavily reliant on the amount of research I need to do. And if I went into the social sciences, I'd just need to find an expert who is interested in collaborating on that, and who knows, who's like pretty good at communication already, to be able to put something together. I think doing it on my own would just take way too long in terms of research. And then in terms of doing, like producing the videos, it can be as fast as 2 weeks. So I did one on superconductivity. That was my last video, and that took 2 weeks, and it was just because I already knew a lot about it because it was related to my PhD research. This one on black holes has taken longer just because I wanted to make sure I was getting the correct information. And so the majority is research and writing the script, because I put a lot of care and attention into structuring the order of what I say, so that I start off with a good foundation and build concepts up off that. I don't want to get too complicated too quickly, because I've seen with some science communication videos, they start becoming a bit of a fire hose of information, which is just fact about this, fact about this, fact about this. And that becomes like quite overwhelming. So yeah, I try and put a lot of care and attention into the writing. I think it's often, because YouTube's such a visual medium, is often sort of underrated or underappreciated, let's say. But I think the writing is really key to making a good video. And then drawing can take upwards of a week. And then animating and filming and editing is just 2 days, something like that. So it's very fast. Yeah. Yeah, it's a good question. I think I have shifted. And you can probably see actually with the map of physics was just the most general lack of detail type description of that I could do without missing any key points. When it got to quantum physics, I really focused on sort of everything that everything that falls under quantum physics. So, you know, the technologies and stuff. When I did the physics map, I didn't talk about technology at all. And then I guess with the particle standard model one, I didn't actually then talk about particle accelerators and experiments and stuff. So I think what I end up covering in a specific video is, the way I decide on that is like what scope I'm choosing. So I think it's just a part of like the writing process is to actually like choose the scope, because I feel like in between quantum physics, the quantum physics video, and the particle physics video, there could be another map, as we're sort of got like going down the chain into more and more detailed areas of science. There could be another one, which is particle physics, which focused on the sort of the research field of particle physics rather than just the standard model, which is like the final results of that. So yeah, I'm not sure I have like an overall idea about exactly what, I don't have overall rules about what I'm going to include and what I don't include. It depends on the video. And in general, I want to do some sort of like a historical context to set up the entry point to a video. And then sort of the body of the subject I'm talking about. And at the end, it's the outstanding mysteries. I think if there was a structure, those would be the three things that I often hit on. Yeah, that was separate. I actually started the books in 2011, so that's like way before I started YouTube in end of 2016 is when I started the YouTube channel. And that just came about because the illustrator, Ben, was a friend of mine from high school, and he studied illustration at university. And he was involved with a publisher who were just starting a new kids book imprint, so like a new kids book publishing house. So they were looking for ideas for of things to do. And Ben really wanted to do a space book. So he just asked me, because I was his friend who did physics and was always banging on to him about, when I was getting into it, like I said at the beginning, when I got into physics, it was because of a popular science show about cosmology. So then I was going into school and like telling him about neutrinos and all that stuff. And I guess that stuck with him. So he asked me to do it. So like lots of people ask me how to get into book publishing, writing, how to pitch things. And unfortunately, I have no idea, because I just lucked into it because of my friend. So generally, the people who are around you now at university are your network. And I think when people talk about networking, they think, oh, you need to go to like networking events and give people's business cards and stuff like that. And that's not true at all. Like, it's the people, your friends now are the people who are going to be doing amazing things in 5-10 years. And so, don't burn your bridges, stick around, keep with them, keep up to date with what they're doing. And that's where a lot of opportunities come from. In fact, my job at D-Wave, I got not because I applied for a job interview, but because a colleague from my PhD program went and worked there, and she recruited me. So yeah, I've got everything from just my friends, which is kind of crazy, but great.
Okay, well, I mean, with that, we're normally at the point we would sort of call it a day. So I think we should all thank Dominic again for an interesting, stimulating talk and telling us about how he does domain of science.